In order to begin our study of batteries, we must first understand the process of redox reactions. Let's start with this interesting picture shown in Life magazine in 1955. Dr. William Shaw uses silver nitrate in solution on a copper Christmas tree. Essentially, copper wire shaped in the form of a tree is lowered into the silver nitrate solution, and what appears to be frost shows up on the copper branches. The base is made of rubber, which is unaffected by the reaction, resulting in a beautiful silver Christmas tree. We'll use the silver tree reaction to study the redox process. Let's begin with the experiment and some observations. In order to perform the silver tree redox reaction, we need silver nitrate, which dissolves in water to give silver ions. The chemical symbol for silver is Ag, and ion is any species with a charge. We also need copper wire, which can be formed into the shape of a coil or a Christmas tree. When the copper wire is dipped into the silver nitrate solution, we can make several observations. The first is that the wire extending above the surface of the liquid is unchanged. A second observation is that the liquid is clear and colorless. And after the wire has been in the solution for 3 minutes, we can see that the copper wire is becoming coated with solid silver, represented as Ag solid. If we let the wire sit in the solution for 8 minutes, we can make some new observations. We can now readily see that the copper wire is becoming coated with solid silver, and the fine needles are growing silver crystals. This is what appears to be the frost on the Christmas tree. We can also see that the solution, which was originally clear and colorless, is turning blue, indicating the presence of copper ions. Copper 2+ ions in solution are a pale blue color. After 12 minutes, we can see that the reaction has proceeded even further. The copper wire is becoming coated with more solid silver, and the solution is turning more blue, indicating a higher concentration of copper 2+ ions. Now let's define the term redox reaction. A redox reaction contains a reduction reaction and an oxidation reaction. An easy way to remember the definition of reduction and oxidation is that Leo the lion says grr. A loss of electrons is oxidation, and a gain of electrons is reduction. Now let's apply this definition to the silver tree reaction. Initially, we had silver ions in solution that gain an electron to form silver solid. We start with a +1 charge, and we add a -1 charge from the electron to give the neutral metal. This is defined as a reduction reaction because Ag+ is gaining an electron in the reactants. The left-hand side of the reaction is the reactants, and the right-hand side is the products. A gain of electrons is a reduction. We also start with solid copper wire, and the blue color indicates the presence of Cu2+ ions. We can see now that copper is giving up or losing 2 electrons. 2 electrons are part of the products, which means they are being lost by the copper solid. Therefore, the copper is being oxidized from copper solid to copper 2+. Once we've identified oxidation and reduction half reactions, we can write an overall redox reaction. There are 2 important criteria. The first is an overall redox reaction needs 1 reduction half reaction and 1 oxidation half reaction. Also, the number of electrons transferred must be equal in both reactions. Let's start with our silver tree reactions. We have our reduction of silver plus to form silver solid. We can see that 1 electron is gained by the Ag+ ion. We also have our oxidation half reaction. Copper solid is oxidized to copper 2+ and loses 2 electrons in the process. We've now met the first criteria. The second criteria is that the number of electrons transferred must be equal. Therefore, to write a balanced reaction, we can multiply the silver half reaction by 2. When we multiply the whole reaction by 2, we would write 2 Ag plus 2 electrons makes 2 Ag solid. Now that we've multiplied the reduction reaction by 2, we can see that we have 2 electrons being gained by the Ag+, and in the oxidation half reactions we have 2 electrons being lost by the copper. In chemical reactions, if something is present in the reactants on the left-hand side, and also present in the products on the right-hand side, they cancel one another out. So the electrons cancel out of the overall redox reaction. For the overall reaction, we simply sum up what's on the left and sum up what's on the right. We can see in the reactants we have 2 Ag+ and copper solid. That goes in the reactant side of our overall reaction. And in the products we have 2 Ag solid and Cu2+. And we write those two species as products of the reaction. We can verify this overall reaction with our observations. We started with silver ions in solution, and they reacted to produce silver solid, which we see the silver crystals growing on the surface of the copper. We began with copper solid in the copper wire, and we made copper 2+ ions, which can be observed in the pale blue color of the solution after the reaction has proceeded. Now try a practice problem. Examine the two half reactions. Chromium solid reacting to produce chromium 3+ and 3 electrons, and nickel 2+ plus 2 electrons making nickel solid. Which half reaction is oxidation? Which half reaction is reduction? And what is the overall balanced redox reaction? Pause the video and write out your answer. The solution is provided on the next slide. Let's start with the first question. Which half reaction is oxidation? Oxidation was defined as a loss of electrons. The chromium half reaction has electrons written as a product, therefore they are being given up or lost by the reactants. The oxidation is the chromium reaction. Which half reaction is the reduction? A reduction is defined as a gain of electrons. The nickel 2+ ion is gaining 2 electrons, or 2 electrons are in the reactants, to make nickel solid. Therefore, the nickel reaction is the reduction. What is the overall balanced redox reaction? For a balanced redox reaction, we need both an oxidation and a reduction, which is the case in these two half reactions, and we also need the number of electrons to be equal. The lowest common denominator between 3 and 2 is 6. Therefore, we multiply the top reaction by 2 and the bottom reaction by 3 and then add them together. We multiply the chromium oxidation reaction by 2 to get 2 chromium solid, reacting to form 2 chromium 3+ and 6 electrons. We multiply the nickel reduction reaction by 3 to give 3 nickel 2+ plus 6 electrons makes 3 nickel solid. We have 6 electrons in the products and 6 electrons in the reactants, so they cancel out, and we simply add together what's left in the reactants and write them in the reactant side of the overall redox reaction, and do the same with the products.